Hello, class. I had a great night's sleep. This is the first lecture that we are doing today. That was the old Sharpie, wasn't it? Is this the new Sharpie? Just a second. Oh yeah, that's the new one. So I'm going to put that there, although I think this one is still working, but I used that for like 3 or 4. Now, the first thing that I want to talk about today, we're talking about maximum power transfer, but you know, I realized, and I wrote this in the comment section of the last lecture, and you probably realized even during the last lecture that instead of it being 6 ohms, I don't know where I got the 6 ohms from, but if you look at how the current would be flowing here in the circuit, you can see that we go through in series a 5 and a 4 ohm resistor. So if I wanted to look at that, 5 plus 4, I don't know how I got 6, but it's 9. And the reason that I wanted that to come out to 9, of course, the current source for Norton's theorem is the same. I didn't do that incorrectly at all. I put the current source back in and everything, and we figured out what the current was going to be, and that's correct, 5.56 amps. The thing that I rushed through and actually just didn't add 2 things together, I had it in my notes as 9 ohms, and so when I finished, I thought, God, I don't seem to remember that coming out to 9 ohms. And I looked back and I thought, God, how could I have added 5 and 4? You know, if we were in class, somebody would have immediately raised their hand and said, Professor Grunquist, 5 plus 4 equals 9. It doesn't equal 6. And I would have been like, oh, yeah, of course. And I also want to point out another thing. Why, and I said this at the beginning, it went for, a long lecture, but I said, hey, I'm going to say that R sub L is 9 ohms now. And I'm going to say that for a reason. And what I wanted to do at the end of that last lecture, although it went on a little bit too long, was I was saying that, yes, this Thevenin's is 9 ohms, and the load is 9 ohms. Why do you think that is? And of course, that would lead me into today's lecture, which is maximum power transfer. So we get maximum power transfer when, right? Maximum power transfer when R sub L equals R sub Thevenin's, right? Now you're probably saying to yourself, and the way that I'm going to prove this, I'm going to prove it both mathematically, but I also want to prove it, conceptually too. What are our power equations? P equals IV equals I squared R, when we use Ohm's law, equals V squared over R, right? So we really only have one equation for power, and that's P equals IV. But when we use Ohm's law, V equals IR, and then we use that as substitutional algebra into that original equation, we get these 2 other equations, don't we? And, if I was to, let's just look at a circuit first. Let's just look at a circuit where I've actually already changed it into its Thevenin equivalent circuit, right? So this is going to be E Thevenin's, and this is going to be R Thevenin's. And then that's going to go into my load resistor, right? This is R sub L. And if we say that R sub L equals R sub Thevenin's, right? Then what would, if we make that assumption, right? So I'm using an inductive. You're probably so familiar with deductive reasoning, and that's something that I would like to sort of take just a second and point out here. What's the difference between inductive reasoning and deductive reasoning? Inductive reasoning takes things that are occurring, it looks at them, and then sees why they couldn't be anything else. Deductive reasoning is usually, that's a standard model that we use in scientific thinking, where we look at a series of connected objective realities, and that brings us through to the final thing, right? So, and that's what we usually do. We deduce things. We use deductive reasoning and the concepts and rules that we use. But inductive reasoning also tells us something. For instance, I'll give you a case of inductive reasoning. Let's say that the ancient Egyptians realized that if they drank water from a swamp, that they would get sick, right? Now, did they deduce that it was microorganisms that were there? Did their deductive reasoning even come up? No, no. They thought that it was evil spirits that inhabited the swamp water, you know, like that. But of course, their inductive reasoning was that if you drank that water, you'd get sick. It doesn't matter what the deductive reasons are. The inductive reasons would be if you drink that water, you're going to get sick. We don't know what the reason, we haven't deduced through scientific analysis the reason, but we know that's going to happen. And so anyway, I want to go back and I want to sort of look at this as an inductive reasoning. So we could see what is the current going to be if I did this. So I sub L, right? And that's going to be the current that is flowing through that that circuit. And we know that R sub L is going to equal R sub TH. So we basically, using Ohm's law, we say that that is the Thevenin's equivalent voltage divided by R sub TH plus R sub L. But we already know that both of those, you know, are the same. So this is just going to be R Thevenin, or E Thevenins, divided by 2 times R sub L. And that equals I sub L. I'm just going to put I sub L there so that we have that as a nice little equation that we can refer back to in a second. Now, if we use that and we look at what P sub L is going to be using I squared R. So I'm going to do that, I sub L squared R sub L, right? And then if we replace I sub L with what we've determined I sub L is going to be, so that's just going to be Thevenin's voltage squared, right, divided by 2 R sub L squared times R sub L, right? So we could write that out. I think that everybody, well, why don't I write the whole thing out? So E sub TH squared R sub L divided by 4 R sub L squared. And of course, the R sub L is going to cancel out with one of those. And we end up getting E Thevenin's squared over 4 R sub L. All right, does everybody see that? E Thevenin's squared over 4 R sub L. You know, we say R sub L, it could be R sub TH, whatever. So I could write that also as E sub TH squared divided by 4 times R sub TH. Right? Either one of those would be perfectly fine, depending upon if we wanted to look at it in R sub L terms or if we wanted to look at it in R sub TH terms. All right, so we've got that now, and of course that equals P sub L. You know, what if we found out we solved it not for I sub L, but we solved it for P equals V sub L over RL, V squared over RL, right? Well, if we did that, I would get, let me just do that derivation. P sub L equals V sub L squared over R sub L, right? Isn't that our other equation? V squared over R, I squared R, or V squared over R? Right? Is that what we basically get? And, you know, doesn't V squared, a second, where did I write this? Oh no, I got it right there. E squared R over, just a second. Let me check something. I want to put an extra step in. Okay, I'm back, and boy, this is not fun turning this thing back on each time, but I very rarely, you know, stop the thing. But so anyway, the point, the thing that I wanted to put in here is, what is V sub L? And V over the load is going to be here, right? V sub L. So the voltage drop across the load resistor is what we're looking at. We're looking at the power in the load, right? So the voltage drop across there, since we know that the voltage right here equals 0, we know the voltage up here has to be VL, right? So if I wanted to find out what VL is, I'm going to write VL up here. I wrote IL out, and of course we've got IL, but let's look at VL and how I would find VL. Well, we know that it's going to be, right, the voltage coming out of the power supply, E sub TH. And then we know it's going to fall across R sub TH, and that we could find out the voltage across here going from 0 up to there is just going to be R sub L divided by, so E sub TH times R sub L divided by the total resistance in the circuit, which is R sub L plus R sub TH, right? We know that R sub L and R sub TH are the same, so this is just really 2 R sub L. Haven't I forgot to, V, well, no, let's just find V sub L. We're going to square it in a second, but this is really then just E sub TH. Have I got that right? E sub, yep. And I could write this S sub L. Yeah, okay, no, that's fine. Yeah, I'm going to make those two. So E sub TH R sub L over 2 R sub L. I could have made it R sub TH or whatever, but you know, and maybe we will do that. But we want to square this now. So this is going to be that R sub L should cancel out with this R sub L, I'm thinking. And that should give me, you know, I could actually just square the, no, that's fine. No, we can still do that. Yeah, let's just stick that in here now. So I've got E sub TH squared divided by 2 squared, so that's 4 times R sub L, right? Oh, wait, E sub TH, wait, what did I forget there? I forgot to square the R sub L I had to put next to it, and then I also, 2 R sub L, E sub TH squared, 4. Yeah, no, I think I think I've got that right. E sub TH squared, and then the R sub L cancels out with one of those. I should have, let me check something. I'll be right back. Oh my goodness. Hi class. No, I've done everything right. I just wanted to check that to make sure that everything you know, looked right. I've got this canceled out with R sub L, so really squaring V sub L is just going to give me E sub TH squared over 4. And then in the denominator, I have R sub L. So I actually wrote it in, but it's the same thing. So it comes to E sub TH over 4 R sub L, or I could say that it's E sub TH squared divided by 4 times R Thevenin, right? Where have I seen that before? I've seen that right here. So it doesn't matter which way I find power, whether I find power with V sub L squared over R sub L, or if I find out power with I squared R sub L, I squared L, I sub L squared R sub L, it's both going to come out to exactly the same thing. E Thevenin squared divided by 4 times Thevenin's resistance. And where you find that, I mean, I could rewrite this, couldn't I? I could rewrite this as E over R. Where is that? V, where is it? V equals IR, or I equals V over R, right? So I could say that this is really Norton's current, right? Because that would be E sub TH over R times Thevenin's voltage divided by 4. Right? And that's true, because wouldn't that be I sub n over 2 times E sub TH over 2? Right? Does everybody see how that works? And so you're probably saying, oh, okay, wow, okay, so they're optimized. Optimized. The power transfer is optimized. So power transfer is optimized when the current is 1/2 of the Norton current and the voltage is 1/2 of the Thevenin's voltage. Now you probably say, hey, well, let's use some inductive thinking here, right? What if R sub L was much smaller than R Thevenin's? Right, R sub L is much smaller than R Thevenin's. If we looked at that, then you would say that P sub L, right, is going to be I squared R. Well, R sub L is smaller, and so that would make P sub L smaller. That's what you would think, right? But hey, look, we've got V sub L squared divided by R sub L. So if I make it smaller, that's going to make it larger, right? If I make it smaller and R sub L is in the denominator, it's going to make P sub L larger. But if I make R sub L smaller, it's in the numerator, well, it's going to make it so, it's competing, isn't it? We've got to find an optimal solution. In fact, what we're really looking at is we're really looking at this type of relationship. Right? And what we want to find is we want to find that point right there. That's a maximum, isn't it? Or an optimum for that graph. So we're looking at power via resistance. How do we find that? First of all, we have to find out what the power equation is, and we've already really found out what the power equation is, but I want to do it for a specific problem. And so I'm going to show it to you so we can use numbers. I find that sometimes, when students use numbers and actually multiply and work the problem out, that, and yes, no, this is not a different problem than you've seen before, because I've got a 9 ohm resistor, and that is going into my load, right? That's going into my load resistor, and I'll call that R sub L. So I've got 60 volts It's going through a 9 ohm resistor, going into my load resistor. And what I want to find out is numerically, what is going to be the, the optimum power. So first we have to come up with a power equation, right, in terms of R sub L. Now we know that that's going to be I squared R L, right? And irrespective of what we get here, it's going to be the same. So let's use E sub TH, that would be 60 volts squared. And did I turn that back on? Yes, I did. only I'm not sure if the things. Anyway, let's get back to this. So we've got this 60 volts squared, right, divided by, let's just look back at the thing, 4 times, but really what I could do is I could just say that it's 9 ohms because I want to find out. Now, here we're not saying that R sub L is 9 ohms. R sub L for the optimal is what? We don't know. So we're just coming up. We're saying it's 9 ohms plus R sub L, right? So we're still looking at the equation like we would get it. Where I sub L is right there. I'm still using R sub TH plus R sub L, right, in the denominator. So that's also going to be squared, right, because that's all part of I sub L, E over R sub TH plus R. So that, let me just bring that down so that everybody can see what I'm using as the equation for I, right? So I squared. Now we know that's 9 ohms. We don't know what R sub L is. We want to find out what it will be for optimization, right? We want to find that point right there. What is R sub L going to be? So first we have to find out the equation of the line, and then we have to take the derivative of that equation and find out where the slope equals 0, don't we? And that will be where our maximum is. And so I want to do it with numbers so that you can see how I'm doing it and working it out. Now, what else do we need? So that's I, and that is squared times R sub L, right? I squared R. So that's the equation that we have. Can we simplify that equation at all? Sure, I could say that this would be 3,600, right? And that's 60 volts, so that's 3,600 volts squared times I sub L times R sub L divided by 9 ohms plus R sub L, whatever that turns out to be. And that, of course, is squared. Now, that's PL. If I wanted, I'm going to put a line down here to separate this. If I wanted to get the derivative of P sub L with respect to R sub L, what would that be? Let's take this derivative. Let's say R sub L is X, right? Let's say R sub L is X. So if I take this if I take the derivative of P sub L with respect to R sub L, what am I going to get? Well, I'll tell you. I'm going to get minus 3,600. Well, actually, I better write it down here. So the derivative of P sub L with respect to R sub L is going to give me minus 3,600 times R sub L minus 9 divided by R sub R sub L plus 9 cubed. All right? So let's put a thing around that too. You're probably saying, wow, how did he get that? I actually went to I tried to do it myself, and I'm sure I could have if I'd taken enough time, but I went to a derivative calculator on the internet, and I found this, and it was very quick. Now, what we want to do, right, in the next step, if that's the first step, right, defining the equation, now we've found the slope of the equation at all points along that line, right? So we're going to set this equal to 0 and then solve that equation for R sub L. Now, look at this. Before we go through a whole thing figuring out what this would be, just look at it for a second. What could R sub L be so that the numerator is 0? Right? That's what we want. We want the numerator to be 0, because it doesn't matter what the denominator is. If the numerator is 0, it's 0. I think everybody can see then that what that's saying is that R sub L must equal 9 ohms, right? Which is the Thevenin's resistance, right? It must. Let's put that in, right? Because this is the derivation. It must equal 9 ohms. It must equal the Thevenin's to get the maximum current through there. And so when you find that maximum current occurs when the voltage is 1/2 and the current is 1/2 of what you would consider it to be for the Thevenin's thing. All right? Does everyone see why maximum power transfer now? And this is good. Now don't live and die by the fact that the load resistance has to be exactly. This is a ballpark figure. Let's say that you figure out that Thevenin's equals 200 ohms. Well, I'll tell you, if you put something in there where R sub L equals 1,000 ohms, not efficient, not optimized, right? Your power transfer, if that's what you're really trying to do, is not going to be optimized. But let's say that you've got something that, is 200 ohms for your Thevenin with the circuit, and you put something in there that is 220 ohms. Don't worry about it. Close enough. That's the thing I want you to take away from this lecture, is that with maximum power transfer, when you're trying to transfer something through there, you want to make sure that whatever the resistance is in the circuit, or whatever type of voltage source you have, and the internal resistance of that is going to mate up with the type of load that you're going to put on that circuit. Does everyone understand that? Why we use this maximum power transfer, and that's why I derived all this. I know that I don't think this has really gone full 35, but I've been giving you some pretty long lectures lately, so I think I'm going to let you off with this one here. Next lecture should be a good one too. All right, I will see you there.